All right. Right, welcome everyone to the first session in the new year. I hope you had a good start into 2024. It's my great pleasure to introduce Xing Wang from the Humboldt University. He's a PhD student in the group of knowledge management in bioinformatics, and he's been working with us at the Comprehensive Cancer Center on a project to leverage large language models like ChatGPT for precision oncology. And he's going to present our recent paper on that. And I'm really happy that he's here and joining us for discussion. If you have any questions, Xing, how do you want to have it? Questions in between or at the end?
Just raise your hands in between. It's fine. Yeah.
All right. So the stage is all yours.
Yes, thanks. Also, hello from my side. Thanks, Manuela, for the nice introduction. As Manuela told you, I'm Xing. I'm a second-year PhD student at Humboldt University to Berlin. And today I will want to give you a little overview about our recent paper, leveraging large language models for decision support and precision oncology. So as Manuela already told you, this is a joint work with the Charité Comprehensive Cancer Center. And in the first, I will give you a little introductions about the molecular tumor boards, which you, I think, are all familiar with, but just that we are all on the same page. So what molecular tumor boards are usually having is cancer patients, which have gone through many first or even second line treatments. So in our example, there's a 56-year-old lung adenoma carcinoma patient who has already gone through chemotherapy of carboplatin and paclitaxel, and now is shown to be therapy resistant. So one has decided to make a penny sequencing or a whole exome sequencing to try to find pathogenic alterations which one may target with precision oncology. So after the penny sequencing, in our fictional patient case, we have identified 4 potential driver mutations which we now want to target. So what happens in the usual MTB workflow is that the clinician will often either know already some therapies or will go through the literature, like databases like VICC or Oncology, or will just make a PubMed and Google Scholar search and try to find new studies, new PubMed articles, which are targeting the molecular alteration at hand. This is often an iterative process, which can take 10 minutes if it's an easy case, but also multiple hours, which then takes up a lot of time. And in the end, the molecular tumor boards then gets a recommendation list. So for example, one could target KRAS, B13D mutations with cetuximab, and evidence maybe a PubMed ID, and here now it's only a case trial, but often phase 3 or phase 2 trials are more convenient. So that was the process till now. So what do we want to do now? As you all know, ChatGPT came around in the December of 2022, and it can be used for a lot of things. And what we asked ourselves is, okay, it can write stuff, it can give you answers about scientific questions. How well does it actually can help us in molecular tumor boards? So in identifying treatment options for cancer patients. And with this, we had 2 questions. So either how useful is it in supporting the molecular tumor board? And the other more difficult question is, can a chatbot like ChatGPT already automate the whole process? So it can really replace the oncologists in this work and help them focus on other tasks. So what we did to test our hypothesis is to generate 10 fictional patient cases in order to have data privacy, so we do not feed real-world patient data into the models. So we ended up on 10 fictional patients. Here you can see a small overview over them. And here are just some examples given. So in the first line, on the right, I've already shown you the lung adenocarcinoma patients with the iterations at hand. And what we are using are large language models, and we are just using them in a natural way. So we just use natural language queries, and we just ask them questions. So really simple questions could look like that you just input in ChatGPT and ask them, what are treatment options for a GNAS 393 mutation? And I really want to give a little quick background on how the large language models actually work, so that we can understand and maybe better assess what they are actually producing. So ChatGPT and all other similar large language models like Llama are autoregressive and always predicting one token at a time. So they are modeling language one step at a time. So for example, with our given query, what is the treatment for the KRAS G13D mutation? This is what the transformer decoder has at the time step 0. And then we would expect him to generate a new token, which is a likely continuations of this question. So we would expect it to start generating the answer. And one possible continuation could be trastuzumab as the first token. And then the large language models take this generated output and feed it again into the same model. So this is the autoregressive part. So in the next time step, t = 1, then we feed the input query and trastuzumab as the next token in. And then we ask the model to further complete the sentence. Then we get another token trastuzumab has. And in the next time step, trastuzumab has shown. And all then we will get a complete sentence, like trastuzumab has shown clinical efficiency in the phase 3 trial ABC. And this is what a large language model in general all will do. So having understood this, now one can ask, okay, but how is this model actually able to infer all these knowledge? And this is where most the training steps come in. So large language models like GPT-3 or Llama are usually trained on millions of documents containing books, web pages, including Wikipedia or other online discussion sites. And in order to perform well in the biomedical domain, usually this also contains pre-training on the PubMed and PubMed Central corpora, which are freely available. So having discussed the model a bit, let's have a look at the large language models that we've actually examined in our study. So we concepted the study in March of last year. And at this time, we chose 4 different models which are available and with different criteria. So first, we chose ChatGPT as one of the most well-known models, and Perplexity AI, which is similar to ChatGPT, but it also adds a search engine on top of it, so it can better refer to literature references. Both these models are closed source. So all the model weights are not available, and it's hard for independent researchers to really always reproduce the outputs exactly as they are. So in order to have more nuanced evaluations, we also compared some open source models against them to see, okay, if we do not want to use closed source models, how well do open source models like Biomed LLM perform? This is a development by Stanford University, which builds up on GPT-2. and Galactica AI, which is developed or which was developed by Meta. So we introduced the model that we had and the data set, and now let's look at what the model actually will return and how does it actually look like conversing with it. And I will have this one example here of the 59-year-old oropharyngeal carcinoma patients who has some 3 mutations at hand, which were likely pathogenic, one PIK3C1 CA mutation, one MAPK1 mutation, and one FGFR3 mutation. And what we did is, now just exemplary, I will give you an overview how the conversation looked like with ChatGPT. So we formulated the query like this. Given an oropharyngeal carcinoma with mutations 1 to 3, what are possible targeted therapies available? And always add clinical trials IDs or PubMed IDs and specify evidence levels so that we can work a bit more with the data to enrich it with some more metadata. And then you can see the output that ChatGPT generated in this case. First, it gave a little introduction what type of cancer it is. And then the interesting part, it described possible treatment options for the mutations. So we, for the PIK3CA mutations, is suggested PIK3CA inhibitors. And in the line here, it showed, okay, alpelisib, urpalisib, or tazolizib as potential options. And then it added evidence levels and PubMed IDs towards it. And then we had a look, okay, does it actually make sense what clinical trials ID ChatGPT has? Because as you know, ChatGPT at that time had no access to the internet. So it really needed to remember all the clinical trials ID. And then if we just look up this clinical trial ID, we see, okay, that's a study assessing the efficiency and safety of alpelisib plus fulvestrant. So in this case, it already is a quite sensible study. Here it is directed toward breast cancer, but yeah, for oropharyngeal carcinoma, there were really no good studies available. And if we compare to the human gold standard evaluations, which we let carry out a clinician of the Charité Molecular Tumor Board, then we can see this was a similar recommendation that it gave. So the human also suggested alpelisib and fulvestrant, which is quite sensible. And it also referred to a study conducted in advanced breast cancer. So you can see for this drug example, ChatGPT already offered some good results. But as you can also see here, the clinicians also annotated copanlisib and RLY2608, and these two were not found by ChatGPT. So you can see they are differing in some kind of ways, and we have complete evaluations later. And for the other mutations, ChatGPT also tried to elaborate whether there are some sensible targets for MAPK1 mutations. Here it explicitly specified that clinical significance was not well established in this kind of cancer. But for MAPK inhibitors, it suggested tramitinib, comitinib, and binitinib as potential options. And if we compare it again to the human annotated suggestions, you can see that the human in this case said, okay, for this mutation, there's not a really perfect targets. So you can already see the differences. So the human said, okay, there's no real targets here. ChatGPT, they provided some possible answers. So we can already see some divergence here. And we repeated the same for the last mutation, the FGFR3 mutations. And again, ChatGPT suggested that there could be FGFR inhibitors like erdafitinib or pemigatinib as possible drugs. And here again, the humans said, okay, this is not really druggable. In contrast, now we can have a look at the outputs of the Galactica model, which was our example for a local model, which doesn't really require the ChatGPT API. So you can just install it locally, and you do not need to feed sensitive patient information to a third-party model. Here we can see that the answers are not as detailed as ChatGPT. And for example, for the PIK3CA mutations, it didn't suggest any treatments in this case. But there are always some differences between each suggestion. So this was the main prompting part, which we did for the different large language models. And for the final study, we also adapted it a bit. So I already told you that we gave the patient's cases in parallel to an oncologist from the molecular tumor board who annotated it. And in the meanwhile, we also fed our fictional patient cases to 4 different LLMs. And for these, we aggregated the results again because they were quite vast. So we once summarized them into clinical treatment options, which are treatment options which were found by more than 2 large language models, and then into another treatment option which had clinical references, so which always had a PubMed ID or NCT ID associated with it. And now the interesting part is that we blinded all the results and then gave all the suggestions to our molecular tumor board at the Charité and asked the clinicians to evaluate, okay, how do you like each option actually? Do you think that the treatment suggestion is likely coming from the large language model, or is it more human generated? So they really didn't know what it was. So how could this survey look like in the MTB, or how did it look like? So here I will just show you an example how a patient was presented. So this is the patient 5 of 10. And here we provided him with the first curated option. So you see all the natural language output already passed from the chatbot. So there's no text, and we just prepared them into a structured output. So in one column, there's a drug given, mechanisms if the large language model provided it, and then the corresponding PubMed IDs. This is the first of 3 options. Then the second option is given here, which again is all drugs. And the third option suggested is here. And as you can see, there's nothing indicating here really which one came from the LLM and which one from the human. And we then asked our members of the molecular tumor board to say, okay, which one of the 3 options is most likely to come from the human and which one from the LLMs. And I will show you the results of this later. So first, some general quantitative results. So we had 10 fictional patient cases, and in total, they had 58 targetable alterations. And as we can see here, in this left diagram, we show for how many of these alterations does the LLM suggest treatment options. The human experts suggested for about 21 of the 58 alterations treatment options. And then we can see the number is similar for Galactica, and for some other large language models, the number is much higher. So they suggested a treatment option for every iteration there was. And also the number of treatment options suggested per iteration also differed for the different LLMs. So the human usually suggested in median about one option per iteration. And this ranged up to 4 treatment options per iteration for biomed LM. So it had quite a lot to say for each iteration where it found something. And from this quantitative result, we now wanted to see, okay, how much do the LLM options overlap and agree with the treatment options that the human annotated? So in this diagram, we treat the human-generated annotations as ground truth, and then measure the F1 score as the agreement between LLM annotation and human expert annotations. So F1 score, in this case, you can just imagine as an accuracy score. So an F1 score of 1 would mean 100% overlap between predictions, and 50% would mean about 50% overlap between LLM annotations and human annotations. And what we can see in general is that the overlap of the large language models was quite low with the humanly annotated treatment options. So 30% was the most, and it went down to up to 2%. So there were quite of differing treatment options which were suggested by the LLMs, which were not part of the human annotations. This is already one interesting insight. And having seen the quantitative results, we now take a look at the results from the MTB survey, where we asked the individual members to rate how likely they would find an annotation to come from an LLM. So in total, we had 43 responses across the 10 fictional patients. So about 4 responses per patient. And here we can see that the humans in large part also preferred the human annotated options. So they didn't know it, but they indicated in 37 of the 43 cases that they prefer the human option, which already shows that it was quite easily detectable in this case. But still, in 6 of the cases, the humans actually preferred the options provided by the large language model. And secondly, each individual treatment option, so the slide that you saw before, were weighted on a scale of 1 to 10 of how likely a recommendation came from an LLM or not, where 10 was most likely to come from an LLM and 0 most unlikely. So both LLM options were weighted quite high. So with a median of 8 and 0.5 to come from a large language models, which is already quite sensible. So again, the humans were quite exact in placing the LLM treatment options higher than the human expert options. The annotations generated by the humans only had a score of 2, which said, okay, this is highly unlikely to come from a machine. So they were quite well in identifying that. So how do we interpret all these results? So as I already showed you, the agreement between LLM predictions and human predictions were quite low, with about 30% F1 scores. On one hand, one can say, okay, LLMs do not perform well, but we can also see that different experts often have slightly different variations in their assessments, whether a drug is usable in this patient case or not. So often there exists inter-annotator heterogeneity. So often if you ask 3 doctors, maybe they have 3-4 different opinions on the right treatments. So this is one argument to not overinterpret the answers. And as we already saw in the example, the results do make sense, which ChatGPT, for example, returned. In a similar vein, our evaluations also is a bit harsh on the LLMs, because we do not really look for nuances, because in the example that I gave you before, the LLM explicitly stated that MAPK inhibitors are not well established in the treatment of oropharyngeal carcinoma. So the tramitinib, cobimetinib, and binimetinib suggestions by the LLM were not really 100% sure. So that's something that we also have to take in mind when we evaluated the results. Another part of the discussion is, okay, we often see that humans consult databases like VICC or Oncology or JAX, DKB to annotate patient cases. And we could argue, okay, maybe these databases are much better than the large language models. So we do not actually need to look at them. But as we can already see in the literature, and also again in our study, is that even though the clinicians consult these databases like VICC and OncoKB, the resulting F1 scores do not show a much higher agreement of the annotations in these clinical databases with what the MTB actually suggested in this case. So here we see that OncoKB, for example, had 32% F1 score, which is minimally higher than our combined LLM score. So we have seen now that LLMs are still a bit far away, but they're actually already usable to get some additional information. But in the last year, there were already some further developments, like ChatGPT version 4. And we just repeated our result with ChatGPT 4 to see whether updates of the large language models will lead to massive improvements in observed results. And what we saw in the example case of ChatGPT 4, in the F1 score, we already see quite a big improvement of ChatGPT 4 compared to the ChatGPT 3 version, about 0.1 difference in F1 score. So we can see that the updated model already provides some better answers. However, what we also see in the case of ChatGPT 4 is that there's a high variability in predictions between the different LLMs. So the drugs that they actually propose are often different from each other. So in the best case, one would expect that GPT-4 and GPT-3 are giving out the same results. But as we see in the overlap, and only about 25 of 80 drugs actually both the predecessor and its successor actually agreed with each other. So this is something that one also has to keep in mind, even when working with the same version of the model. Sometimes under the hood, the ChatGPT version differs, and then the results can also be a bit different. So what do we conclude now from our study? In the first, we wanted to answer the questions whether the large language models can support molecular tumor board in its decision process, and secondly, whether it can already fully automate it. So for the second answer, we can already provide a clear no. Large language models, as we have examined in our study, lack the thoroughly backed evidences to fully automate the decision process. This was one thing that the MTB survey members often remarked, because often the clinical studies which ChatGPT referenced were either already closed or were not completely relevant. So in order to get better results, the MTB cannot fully rely on it. But for the second questions, we can provide a yes. So large language models like ChatGPT can help guide clinicians during the annotation process. There were some examples where ChatGPT or the other models provided therapy options which the human expert didn't find. So for example, in the salivary duct carcinoma patients with HRAS and PAK3CA mutations, they suggested anti-androgen therapy, which the human expert didn't mention. So in case sometimes the human is missing something, then the language model can remind that, okay, maybe there's another different treatment option that you might consider. And the second part is, if you're actually conversing with large language models, important to be as specific as possible with your prompt and to try out different prompting strategies, which may change. For example, for ChatGPT, it's often helpful to tell him what is the setting in which he has to answer the question. So a useful prompt in the beginning is, you are a specialized oncologist in a molecular tumor board looking for treatment options for a given cancer patient. Try to answer the questions based on your internal knowledge, and then you can start your conversations, and then the chatbot usually gives out quite sensible answers. And last but not least, even when you are using large language models to support your process, always double check your results and do not rely solely on their output. And last, still one point about the local models, which we examined. Local models like Galactica, performance-wise, already offered good performances, but often they lacked expressiveness in their answers. So as you see, ChatGPT was often able to provide clinical trials ID and PubMed IDs, which wasn't the case for the smaller local models. So this is something which still needs to be improved upon for these local models if you want to use them in-house. So what do we want to do in the future now? After having conducted this study, we've evaluated that they could provide quite some benefit in fictional patient cases. And in the future, we at the Charité Comprehensive Cancer Center and at Humboldt University want to conduct a prospective study for real patients to see whether we can also see a benefit in the real world case. So that was my presentations. Again, special thanks to the Charité Comprehensive Cancer Center and Manuela for the support of the study. and also to my supervisor with Lisa at Humboldt University and the core unit bioinformatics at BIH.
Yeah, thanks so much for this detailed study. I assume there are a lot of questions, and I'll open the floor. Just raise your hand or maybe open your video and start questioning. If not, I can maybe ask one, which is always on my mind, is how would you improve the large language models if you have additional information, or how would you do that from a technical side?
So yeah, from a technical point, I would try to embed the large language models more in real-world knowledge, so that it can directly access the latest clinical trials and PubMed IDs, and then answer based on a given context. Because till now, usually all the knowledge is stored in the internal model weights. So you cannot really make sure that the model is actually not hallucinating and make stuff up just by its own stored data. And if you could just make a direct connections to PubMed and clinical trials, then we can be more sure that we get high quality answers.
I have a few questions for you too. Thank you so much for that. That was really informative and cool, and something that I think a lot of us are interested in exploring too. So one of your main points was that large language models cannot automate output for molecular tumor board. Do you think that in your opinion, do you think that's always going to be the case, or do you think that there, in the future, large language models can potentially automate these things for the molecular tumor board?
So I think if large language models actually incorporate all the stuff that I said, so they really provide you the exact text span in PubMed, which they found, and if they're able to do all this and they always have access to the latest literature, I think maybe in 2-3 years, they can be much more helpful in providing. Whether they will really fully automate it, I'm still be a bit wary of it, but I see there's a high potential that they become much better.
Right, and one thing I've noticed when using things like ChatGPT or Perplexity is that, and you mentioned it too, is that some of the information that you get back is incorrect. If you go to the sources and kind of double check some of these assertions,
Yes.
You've looked at this a lot more than I have. How frequent do you think that happens where you get some incorrect data?
So in the earlier versions of the models, so I think 1 year ago, it was quite a common problem, I think, where maybe 30% to 40% of the output that ChatGPT provided linked to studies which were either incorrect or didn't actually exist. But I think in the recent times, this got a lot better. Also, in the case of Perplexity and ChatGPT, they now really have linked you to references. So they really link you to real web pages. So often case, the real web page contains the text which they actually refer to. So they already integrate some of the stuff that I talked about. So I would be much more happy to rely on them and have more confidence in them.
Mm-hmm. Cool. And what, and lastly, this will be my last question. What kind of advice could you give to people on this call that might want to familiarize themselves more with these large language models or different interfaces of artificial intelligence in their practice?
So I think in the core, it boils down again to the things which I listed here in this slide. So try out different prompting strategies, try out different strategies how to converse with the large language models, because in some cases we'll be not so willing to give you an educated guess. But if you provided the information that, okay, you are a specialized oncologist, then it will be more likely to give you some results. And in the second case, as you already said, I would suggest trying out different models, as you said, for ChatGPT, Perplexity, or other models which are out on the market, to give a feel where they differ, whether they all output the same result, so that you can be more sure about the answers. But in the end, always double check results, because, as you already said, there still will be some fictional stuff made up.
Thank you.
Thanks a lot.
Hi, I have a follow-up question actually concerning that point that you're saying that like different models didn't align in their prediction. I was wondering if you also looked at how the same model might not always provide the same answer. Like in my work, what I looked at, sometimes I ask a question, and if I repeated it 20 times, I will have 20 different answers. And so I was wondering if you took that kind of variability into account, and if you saw that even if you look at only one model, it's actually not even self-consistent.
Yes, this is a good point that you raised. So I've also encountered it in our studies that the models sometimes differs in between its answers. And in the end, we just said, okay, we will just take one checkpoint and then evaluate its answers. But mostly for ChatGPT, for example, I found it was a bit more consistent than other answers and other models. And it often also depended on the questions, how you phrased it. If you phrased it completely differently, then you could get 20 different answers. So that was also important to keep in mind.
Okay, thank you.
Maybe I have a question which goes more in general also to the round. What's your feeling on how to use large language models with real patient data? What's your experience in your university or clinic to actually provide this real world data and sensitive data to ChatGPT, for example?
Sorry, is it addressed to me?
Or just in general, anyone. It would be interesting. I mean, it's very strict in Germany to deal with patient data and send it anywhere. Yeah. And would be interesting to see what everyone else is thinking about this kind of use of these models.
Like at Mayo Clinic, they have their kind of industry protected OpenAI access. So there is an API protected, and I think it's compliant from like a medical point of view. And I think also what I'm using, and the majority of my work is just using like smaller models that you can actually run on a cluster. And this way you do not have this issue. But yeah, it's really, I think, important to consider that for sure. And I would not trust any of the industry, like kind of LLMs that are industry owned for handling this kind of data directly.
May I ask which models are you using on your own cluster? What are your experience with them?
So on your Hugging Face, you can access a few simple ones. So usually I look at the smaller models because they take like 7 billion parameters is already quite a lot to fit on a cluster. So usually I just use as the smaller one. So there is llamas, there is a few of those that you can access there.
Thanks. Are there any other questions? Damia, go ahead.
Yeah, thanks. Thanks, Xing. That was a great talk and great summary. So I have two thoughts on the whole thing. So first of all, Xing, maybe you can also comment, because what I thought was really interesting also about this work, which you highlighted, was that a model performs better if it has a larger data background, in contrast to a model that is maybe PubMed specific, which I thought was super interesting, that it's not so much a highly trained model, but more or less like a broadly trained model that seems to perform better, which I thought was very interesting. Maybe you could comment on that?
Yeah, this is an interesting phenomenon that one has observed all over text mining and these large language models, is that the larger you make the model and the more data you feed into it, the better it performs. But I would also not say that, for example, in the case of the models which were trained specifically on PubMed, that the general models were in the disadvantage because they had all the general domain knowledge and PubMed as well. So they also saw PubMed, clinical trials, and then they also saw FDA and EMA pages on the web. So in this case, they actually also had the benefit to not be so fine-grained just on PubMed.
So it's not just size, but it's also size plus specificity, probably, right? So yeah.
Exactly.
And the other comment that I had was, and that's just a general thought, we typically, I think all over the biomedical sciences, but in precision oncology in special, we spend a lot of time to try to structure unstructured data. That's what we do in clinical medicine and with molecular data. And that is a lot of human work and effort that is being put into it. And I just wonder if those large language models actually make it unnecessary to create structured work, or will they eventually help us to structure the work for us? So that is one thing that I don't really have an answer to that, but that is something that I really take from this work, where I wonder if we will eventually need structured data, if we have machines that can sort of structure data at the time that we need it.
Yeah, this is also an interesting thought that we also encountered in the study, because as you saw, the output of all the large language models wasn't really structured. So it also took us quite some work to make it into a structured format. But I think that LLMs can also support this process, because you can also provide them prompts to extract the knowledge from the structured text and put it into a format as we specify. So this is something that I also want to experiment in the future, to make the outputs more structured and easily usable for clinicians and for us. Yeah. But I think it's still not super highly explored part of the field, because mostly now we are just training the models to generate language as we are speaking, and not in a specific artificial way.
So you say you would have to retrain a model actually to get more structured data out of it? Or can you
Depends on
build
the model.
around?
Actually, you can already give ChatGPT examples of how you want an input and an output, and then you give him an example how to structure it, then he can help you with it. So this doesn't really involve completely retraining.
That's pretty cool. Then you give it a template and it essentially fills in the template for you.
Exactly.
Okay.
Yes.
Neat. So I have a question about future work to be done on this. I noticed that, a lot of your work had to do with finding therapy opportunities for patients based on their genetic makeup of their tumor. Are there any other aspects of clinical relevance that you're actively looking into, or are you going to continue to focus primarily on finding those clinical trials and treatments?
I think the main focus now will be more on continuing this work. So finding clinical trials and on the molecular profile. Yes.
Cool.
What were you thinking of going into which direction?
I was almost thinking there's a lot of different opportunities. My mind went a lot of different places during this talk about, you know, is there an opportunity to like give a list of variants from, let's say, a carcinoma of unknown primary and see if a large language model could fit it into a diagnostic bucket at some point, much like what methylation can do in terms of finding similar attributes within the tumor, or can you get a list of genes by kind of dictating a rare tumor or something like that. So I think that there's a lot of opportunity that can be tapped into. I think the most like immediately actionable and clinically relevant route is the one that you're looking into with therapies. But I think that there's just so many possibilities of things that could be explored.
Yeah, I like your idea for cancer of unknown primary to look into those. But I believe one thing which we haven't really looked into and which is probably worthwhile going into is into interactions and reverse resistance mechanisms, which could be predicted if you know the full profile. And we do have this one example of the androgen receptor inhibitor, which wasn't picked up because we didn't have the staining for that. We just had the molecular profile. Yeah, so maybe it's worthwhile going into the complex combinations of the molecular profile.
And that's a really distinct gap in knowledge bases, is interactions. And I mean, there are places that try to do that in a quite manual way, but I'm wondering if large language models can maybe feed into some of our knowledge bases or complement some of our curation techniques to, you know, highlight some of those associations. Yeah, that's really great.
I also wonder to what extent it may help or not help with variant interpretation itself for less common alterations. The ones that you were showing were all fairly well established alterations in terms of whether or not they're oncogenic anyway. And there are, as we all know, a lot of variants that don't fall into that category. And have you looked at all at how it does with edge cases in terms of variants themselves?
I didn't look specifically for this study, but I think this is also a really interesting topic to further delve into, really let the LLMs also do some work that the pathologists actually do now.
Yeah, I mean, that's certainly a case where humans disagree quite a lot.
Yeah, and all we can do, right, Cheryl, is to like present everything that you find on some of these edge cases. I know that I've tried to use some AI on some fusion cases where I didn't find much in a literature search, and in some cases it helped immensely because of the summaries that come out of it. Although with the caveat, you should look into every resource that they give you, because I think that these data models are trained in like a positive feedback loop where they're trained to have associations and not have associations. So it's, yeah, there's a big caveat there, but I find it helpful, and one other route to go in those cases where you really want there to be an answer.
Yeah, I think even with the therapies, what Xing was saying was that it errs more on the side of over-inclusion than under-inclusion. And in almost all cases, I think the physicians had shorter lists, and that was how they could all tell which ones were coming from the computer and which ones were human.
Yeah, that is also a way of how we summarize the information. as Beth said, or also large language models, they don't know how to say, no, I don't know. They're usually giving an answer anyways. And sometimes the answer was more like, oh, well, I don't have anything on this specific alterations, but if you look into a different alteration, we could provide that and that treatment. And we try to pull out only relevant treatments, but maybe we picked up some more than were actually available. Yeah, because the results are really verbose, and I guess the same is true also for variant annotation in general, like whether or not this is an oncogenic variant. It's better though with ChatGPT 4, so at least it doesn't hallucinate on PubMed IDs or trial IDs anymore. Maybe it's not giving the best ones, but at least not made up IDs. Okay, so thanks so much everyone for the discussion. Thanks Xing for the presentation and your time here. It was really interesting to see. Yeah, have a great day everyone, and we'll see you again in 4 weeks for our next seminar.
Great. Thank you so much again.
Thank
Thanks
you.
a lot for having me. Have a good day.
Bye-bye.